This talk is done by Petra Heck. Petra Heck is a researcher and teacher at the AI and Big Data department of Fontys. She specialized in trustworthy AI engineering and software engineering. And she was even nominated in the top 5 Women in AI Awards of 2023. So please give a very big applause for Petra. Succes.
Thank you. It's really great that you're now all very energized, because you will need this energy to listen to my important story. Thank you for introducing me. I think I will need to correct a few things, because I'm actually a senior researcher in the Fontys Knowledge Center Applied AI for Society. And this is a really cool initiative that we started 1 year ago, where we gathered all the Fontys institutes. So it could be from the Sporthogeschool, so the Applied University for Sports. Could be we have a Applied University for Law, a School of Law, and we all work together to establish applied AI for society. And you see our slogan, so to say, is exploring the future of trustworthy AI. And that really matches also the theme of today. There's a lot of AI models, cool AI stuff out there, but how to really apply it in practice, how to get it working. Oh, sorry, the other way. I see. I see there's something different here than I see there. Yeah, but if I click next. Oh, yeah, sorry. A little bit about my personal background. As you can see, I actually have a software engineering background. So I studied computer science here in Eindhoven. And I worked as a software engineer and later a software quality consultant. And in 2004, I briefly worked at the Eindhoven University of Technology in the laboratory for quality software. That was when I became interested also in quality. So I have a background in software engineering and a background in quality. And when I started working at Fontys in 2012, I had the opportunity to continue that background in a PhD. So I did a PhD in computer science at the Technical University of Delft. And that was still just software engineering, in fact, requirements engineering, so thinking about how to specify software systems in a proper way. After my PhD, I really saw applied data science. We called it applied data science back then. I saw it coming into the education at Fontys University of Applied Sciences. We had more and more students, ICT students, that got assignments to build data science-related software systems. So because we saw that, because we saw companies asking that from our students, we asked ourselves the question, okay, but if companies ask that from our students, we should know how to do that. And then it started 4 years ago, and it gradually evolved from applying data science in practice to now everybody's talking about building AI systems. So the question I currently try to answer is how to build trustworthy AI systems. And you see at the picture over there the link between data science, because I'm actually not from data science, I'm from software engineering, but somehow I try to make the bridge to the data science, because we need the data science and the software engineering to build intelligent systems. We need them both. And that's actually also what this slide represents. In academia, we see a new discipline. Actually, this year, they organized the second international conference on AI engineering. And AI engineering is actually the combination between machine learning, data science, and software engineering. So you need both. And here I say again AI engineering, but for me AI is almost synonym to machine learning, because I'm looking at narrow AI, as was said in the previous presentations. It's using machine learning to implement AI systems. On that side, you see also a very important picture, because where academia talk more about AI engineering, in industry, the term MLOps, machine learning operations, is often used and found. And as you can see, from a software engineering perspective, MLOps is like an extension of DevOps. The last two cycles is the development and the operation of the software in production. But from a data science perspective, it's an extension of data science, basically, because the first two cycles, collecting, gathering the data, and building a machine learning model out of it, it's good to be aware that after those two cycles, you also need to do something to put it into production, to embody it in a software system. So also the term MLOps is something you should keep an eye on. AI engineering, MLOps, basically more or less the same. Because like I said, you have data and models, that's the data science part of your system, but you also will have a lot of code, training code and test code. I heard also Rose saying she is a data scientist, but she does a lot of coding. So I think most of you should recognize that. But also, in the end there you see, before you can deploy your models, you need also a lot of application code, actually more code, to make it possible for the end users to use your model. So that's also important to keep in mind. To have AI in production, we need data, we need models, and we need code. These three things. I sent an updated slide. Are these not my updated slides? I missed one slide. Okay, doesn't really matter. It's not too important, because I made a separate slide out of that blue picture up there. I put it on a separate slide to make it more easily readable, but it's still there. In fact, for software engineering, we have been thinking about quality of software systems since ages. When I was working at the university in the Laboratory for Quality Software, we used a quality model called ISO 9126. Probably most of you didn't hear about this before. But now the newest version of it, it's the ISO 25000 quality model. And basically what it does, it's a model for software product quality. So it identifies which quality properties are important for software products. But these are, if you can read it, on the top blue boxes, these are things like usability, performance, security, all well-known properties. But in software engineering for ages, we have thought about, okay, these things are important. How can we measure them? How can we ensure them? How can we design software such that they fulfill those kind of properties? So it's there since a long time. And then my question was, okay, but if it's there for software, I have, from 2019, I've been analyzing the difference between rule-based software systems and AI-based software systems. So does that model still hold for AI-enabled systems, or do we need something else, or something different? And I'm still in the preliminary phase of this study, but the first thing that I did was to see if we are missing any important quality properties that we need for AI systems that we don't have for rule-based software systems in the ISO 25000 standards. And for that, I use two important sources. This one, the Ethics Guidelines for Trustworthy AI, was written by the committee of the European Union. And this is a really valuable document, by the way. Even if you're not a software engineer, you should read it, because it's about how to build trustworthy AI, but also really the technical perspective. So not just the management story about, oh yeah, we should do this is really important, you should avoid bias. No, it really has a checklist about how to do it. It really has a lot of things that you can implement in any project. So they have 7 requirements, they call it, 7 requirements for trustworthy AI. And on the other hand, I found a really nice literature survey of academic literature on testing machine learning systems. So it's academic, and a lot of things that are not really ready to apply in industry yet, but it does have a nice overview of what is testing of machine learning systems. And from that overview, I took a list of properties where they say, okay, this is the properties that you should test a machine learning system for. And of course, yeah, correctness, overfitting degree, these are the things that we usually do, the performance of the model. But it also includes the privacy, security, robustness. So combining those two stories with the already existing model, I came up with let's say, a quality model for trustworthy AI. So these are properties, and I heard them already a number of times also in the previous talks. We all recognize this, but we all name them. We all might name them a little bit differently, so it might hinder the discussion. And something that we also should learn from the way software engineers look at quality. They say, okay, we cannot do this all at once because it will cost us too much money if we want to do all of this for one single system. It's not possible. We have to balance. And for each system, before we even start modeling or collecting data, we should probably ask ourselves, okay, for this particular system, which of these properties are important? And where do we want to spend our time and money on? What do we need to achieve? Keep in mind, for us, these are the properties that you have to add to the ones that are already there in the ISO 25000. So things like usability, they are not in my picture here because they were already in the existing model. But of course, they are still very important. But you can see some usability-related properties, like collaboration effectiveness. And that's what also Tina was talking about, the human-AI interaction. It's really important, and it's quite new that we have to keep an eye on that for AI systems. Human autonomy, the system shouldn't threaten people. So you find a lot of relations with existing properties, but they're also still important. And to illustrate this, I would like to tell you a story about one of the systems we are working on at Fontys Applied University. It's the Flower Power wildflower monitoring platform. It's actually a project by one of my colleagues, Gerard Schouten. He's a lector AI and big data, so that's the confusion. I work with him in this lectorate. It's a research group, basically. Because I work at an applied university, we don't have professors, but we have lectors. And he is actually also a nature photographer himself. So he likes to take pictures of flowers in the wild. And out of that, he came up with the idea. He's working on a big project together with biology researchers in the Netherlands. Because basically what biologists do, normally they go out in the field and they count flowers. And they need this information because they need to have a way to say something about the biodiversity. How well is nature going in a certain area of the Netherlands. And for them, it's really boring labor to go out in the field and to count flowers. So they don't really like it. So they were looking at a way of automating this. So we are, together with, for example, big Dutch research institutes like Naturalis, we are working on a way of automating this flower counting, which for us as a university, it's a nice case study because it offers us a way to practice deep learning techniques on the pictures of the flowers. And yeah, we can actually help the biology researchers in the Netherlands with that. But currently, at this moment, basically we only have this trained model. So yeah, we have of course we have a data set of 2,000 images, and we have trained a deep learning model on that, but that's it. So we have Python notebooks with this data processing and the trained model. And now we have a plan. If we really want to get it out there, help the biology researchers with that, we need to make a full system out of it with a user interface where they can upload new images and get back the annotations and all sorts of ideas we have about that. So now let's think about, okay, we are in the beginning of this project, so we need to think about the requirements, the quality requirements for if we really want biology researchers to be using this platform. The first thing that's different between a rule-based, the old way we used to build software and the new way we build software with machine learning is the fact that in classical programming, we program the rules ourselves. We as software engineers, as programmers, we program the rules, so we are quite sure what happens. In a machine learning system, the algorithms learn the rules from the data, from the examples we feed. So that's already one thing to be aware of. If we give bad examples, we will learn bad rules. We all know that. So this fact that in AI systems we train algorithms to learn rules from data gives us already three properties that are different from old-fashioned rule-based software systems. So we should worry about learning the correct rules. We should worry about learning rules that also will hold for data we don't know yet. So we should, that's the overfitting degree that we want to be as low as possible. And we should take care of the fact that people could try to attack our model even, to give wrong inputs or slightly changed inputs, and that could lead to effects that we really don't want. That's really the malicious or the security part of data science, that we should make our models robust against these kind of adversarial attacks. So applying that to our flower power system means that we should put some numbers on, okay, what do we expect from the performance of this model? And then you start thinking about, okay, maybe we should, because when you are just training the model, you just have these 2,000 images, and the only thing you're interested in is getting the performance as high as possible. But then you only do that for these 2,000 images that you have. So if you want to do it in the wild and upload any picture of any flower, you should start thinking about, okay, what are actually the boundaries of where I want my model to perform well? And that's why we came up, for example, with a requirement saying, okay, we want our model only to detect flowers that are at least 50% visible, because you could have flowers on the edges of the picture. And we want them to be a little bit big. On the picture, it should have at least 1 centimeter head size, otherwise we cannot see it really on the picture. And we should also think about the generalizability of what we learn. And that made us think, okay, we have these 2,000 images, but they were all taken with one specific camera. So maybe if we really want to put the system into production, we should make sure that our system works with different types of cameras or in different types of landscapes. So thinking about this up front made us realize, okay, we should maybe enhance our data set with different types of images so we can test these kind of generalizability properties and find out where are the boundaries, when does it stop working. Another thing that's different for AI systems than for regular software systems is that we have these, I hope you all recognize this kind of process. It's the crisp DM, and we at Fontys, we use the IBM data science methodology, which has been, is a kind of an extension of crisp DM. One or two steps they have added the steps or made some different descriptions for the steps. But at least what you can see here, and what you all know probably, is that there is a huge part of the process where you have these data preparation, data processing, understanding data, exploratory data analysis. So you're working with huge data sets, and yeah, it nicely also fits your story. You try to understand what's going on inside my data, but it's almost impossible for us as humans to do that because the data is so big, or there are lots of different data sets that you're actually trying to connect. So that leads to potentially to problems. That's also what we heard before with fairness, bias problems, or with privacy, that somewhere in your data there are some hidden personal properties. So the obvious ones, okay, yeah, we all know that we should anonymize our data, etc. But think about this example from, I think it was from Strava or something, that they said, okay, everybody can look at our data set, we anonymized it, but then if you look at the data from Strava, you could see people running around certain areas, so it was not so difficult to find out where they're living, actually, because yeah, if you always start at your home and you end at your home, so yeah, bit of a mistake. But so privacy is not just about anonymizing data; it's also thinking about, do I have some kind of hidden properties maybe in my data set that could violate people's privacy? Applying this to flowers, you would say, okay, yeah, it's flowers, who cares? But actually, my colleague, he said, yeah, but think about these flowers. They also have kind of privacy issues. Because he had many examples of, if somewhere there would be a really rare orchid, he would have many examples of other nature photographers. They are in a kind of a group or forum, and they would tell each other, okay, but it's there. You can find this really rare orchid, you can find it there. And then everybody would go there, and then eventually it might even happen that the orchid gets trampled, because so many people come there and try to photograph it. So even for flowers, privacy is an issue, and we realized only through this exercise that we did of going through the properties one by one and saying, okay, yeah, but it is an issue. So maybe we should do something with the exact GPS location of the flowers in our system. Because if you take a picture would have kind of metadata, might have metadata about the GPS location where the picture was taken. Maybe we should protect the GPS data of the picture. So that's something really surprising also for me, what happened when we did this analysis of the system. And also fairness does play a role for flowers. So we also have underrepresented species in our system. So we should do something with that to make the data set well balanced. And the last thing that really well relates to the first speaker of the day, but also even the second, there is a lot of interaction needed, the human in the loop, the fact that we need a user that operates the system, but also that the system should support the user in making decisions. In this case, in our system, we have different type of users that we foresee. The biology researcher, as I said, but also maybe the policymaker, the one maybe working at a municipality and interested in, okay, what's going on in my city? What's the biodiversity scores of the different areas in the city. Where do we need to spend more attention on? They should have a kind of dashboard looking at the different biodiversity counts in the city. There's also a plan in the future to make something that makes it fun for citizens to upload pictures of flower fields so that we can collect. We want to do some kind of crowdsourcing because it does also take quite some time to go out in the field and make these pictures. So we were thinking of a way of making this fun for everybody to do. We also see this, we also consider a very important user the data scientist or AI engineer that wants to improve the models. We should also think about these types of users, how you can use the system to upload improved versions of models, for example. And if you look at the human-centered perspective, you get the last 4 properties that are important for AI systems and were not so important for regular software systems. That's the collaboration effectiveness, that the system and the user should work together in an effective way. Of course, the explainability, you see that everywhere, explainability, transparency, interpretability. We need that for a system to be effective in the cooperation with the user, and of course, very important also for the trust, to be able to trust the decisions that you make together with the system. Controllability, you want to have some kind of control over the system as a user, if that's an important feature of the system. So again, translate this to the flower power system. We came up with the idea, okay, it's nice to be able to upload a picture and to see which flowers are, that's in the experimental phase, that was really important. We wanted to upload a picture, see the predictions of the model with the bounding boxes, and then see if it's correct or not. But if you think about the future, where the biologists are using the system, they would be more interested in uploading, for example, because in the meantime, we're also working on a drone-based system, that a drone can fly over an area and take pictures automatically. And then the biologist would really like to upload 100 pictures at once and get a nice table of, okay, in this field we found that many flowers of that type. And so we need this kind of batch mode if you think about it. And the explainability, of course, that's more for the AI engineer to understand where the model is doing right and where it's doing wrong. You need kind of explainability features like saliency maps. And for the controllability, we want to give the biology researcher some control over what the system is doing. And in this case, it means, most of the time, it means that we want the user, because the biologist is actually the expert about what kind of flower is this. The system gives some predictions or scores, so the user should be able to be in control and correct these annotations. So that was the complete discussion of the model with the example of one of our projects that we're working on. We're working on many more projects, but we want to keep applying this model and see, okay, does it still work? Do we see new quality properties coming in? Because actually, 2 weeks ago, I discovered that we might want to add a reproducibility property, because we do see that that's also something really more important in AI systems, where we're not really sure what happens inside. So we want to be confident that each time we do the same, we put the same things in, we get the same things out. And also for accountancy and control, this reproducibility might be one of the properties we will soon add to the model. So that's one thing. We see the model as a dictionary for defining the quality properties of your system. And then you do not need to define all of them, but you need to think about it and prioritize and balance them. What requirements do you need from your system? And our final idea or goal is that we can also extend, so we have the model, okay, this is just a list of properties that you need to think about, but we would like to extend it with tools and things that you can really help you to detect problems with certain quality problems, but also prevent problems from happening. So it will be more than just a list of properties, but actually a toolbox for building trustworthy AI systems. And then if you're building one of those systems, you go to the toolbox and you select the tools that you need for your particular system, because you know which properties are most important and where you want to spend your time and money on. So that was my story. Thank you.
Thank you very much, Petra. It was very interesting, especially with your example. I've never ever thought about the privacy of flowers before. So I think for a lot of people it was, but actually it was a good thing, because some people are kind of laughing about privacy, but now you realize, like, even for flowers it's very important. I just have one question for you. So you showed us the AI trustworthy requirements in this, like, the flower figure. And do you feel like, I mean, I'm kind of asking you to generalize a bit, but do you feel like there's one of the requirements which data scientists very often forget, that you as a software engineer feel like, guys, come on, don't forget this again?
No, actually I have another type of story. It's not about forgetting, but it's about focusing too much on, for example, model performance. Because if you're in the early stage and if you're in the data science stage, yeah, you're used to focusing on as high performance as possible. But I know of a case where, for example, the real business case was, okay, we need to ship a bag of seeds, and out of this bag, the maximum of 5% of the seeds can be faulty. That's because that's what we agreed with the people that buy the seeds from us. So actually, in practice, it means that you, if you have this 0.95% of accuracy, you actually should stop. Because after that, if you get it up to 0.98, you're costing money. The company is losing money, because it means they're shipping high quality seeds, where they could even take out some of those high quality seeds because they can put in some faulty seeds. Because, yeah, why should they do better than they promised? My message is not about not forgetting any of these properties, but my message is really about analyze these properties one by one before you start. You can do this quickly in your head to see, okay, what are the actual goals of the project? And it might not always be the model performance.
Okay, thank you. Dankjewel.